Welcome to the 26th session of Flipped Classroom for Calculus. Today we're going to talk about linearization and differentials. What's that, you might say? Well, click the slide, you'll find out. Some functions are tough to find their exact function value. What if we could use the tangent line to a function at a certain x value to approximate the value of that function f of x at an x value that was near? Okay, this process is called linearization, and it's really pretty simple. Picture's worth 1,000 words. Okay, in this case, if you look at the function y equals x squared, you see there's a tangent line that's drawn at the point 1, 1. Okay, the derivative of y equals x squared is 2x. So therefore, the slope of that tangent line is going to be 2x. If you look, okay, I could approximate the value of the function at some x, let's say right where the pointer is here, close to 1, by using the value of the tangent line, the y value of the tangent line. This is the whole idea behind linearization. Okay, in this case, the tangent line equation equals y equals 2x minus 1. In other words, this red line's equation is 2x minus 1. So I could approximate the value of the original function x squared by using the tangent line, as long as the x value that I'm looking at is close to the original x value. Okay? Here's an example. Okay, remember the picture before. Tangent line equals y equals 2x minus 1. If the point 1, 1 on the previous slide is written as a, f of a, where a is 1 and f of a would be 1, then we could express the tangent line using this equation. F prime of a, meaning the slope at a, equals f of x minus f of a over x minus a. Okay, this is nothing new. I'm going to solve for f of x, however, and when I solve for f of x, I get f prime of a times the quantity x minus a plus f of a. So f of x would equal f prime of a times the quantity x minus a plus f of a. We will call f of x the linearization L of x. Okay, that would be known as the linearization of f at a, and is defined as L of x equals f prime of a times the quantity x minus a plus f of a. Okay, coming up as an example. Again, L of x, f prime of a times the quantity x minus a plus f of a. Let's find the linearization of f of x equals 1 plus x to the 1/2 at x equals 0. So a would be 0 here. Step 1, find the derivative and evaluate at x equals 0. Well, f prime of x is 1 over 2 times the square root of 1 plus x to the 1/2. F prime of 0 is 1/2. Find f of a, because you need f of a. F of 0 in this case would be f of a, and it equals 1. I found that by sticking it into the original function. So therefore, according to L of x has to equal 1/2 times the quantity x minus 0 plus 1, which reduces out to 1/2 x plus 1. Okay? Oops, disregard this f.01. Okay, that should not be there. Disregard the f.01. Okay, this can be used to approximate the original function at values of x close to x equals 0. Here's the f.01. Okay, I can find the function value at 0.01, which would be rather difficult by sticking it into the original equation if I did not have a calculator. Okay, but I can find this function value by using the linearization, because f.01 approximately equals, here's my tangent line equation, 1/2 times 0.01 plus 1, 1.005. Okay, now just to see how close we are, let's use our calculator and stick 0.01 into the original equation, 1 plus x to the 1/2. You get 1.00498. So our estimate is pretty dang close. It's to within 1,000th of to within 1,000th of the correct value. So this is a neat way to evaluate functions that may be complicated by using the tangent line equation. That's all linearization does, okay? It's pretty simple. The second part of this section is on differentials, and we're just going to touch the surface of differentials here to get us started, and then in the second video we will deal more in depth with them. Okay, if f of x is a differentiable function, that means it has a derivative at all points in its domain. The differential dx, okay, is an independent variable, meaning it's the one that you change, okay? The differential dy is dependent on dx, and it is defined as dy equals f prime of x times dx. Okay, this is really pretty simple. Find dy if y equals x to the fifth plus 37x. All you do is take the derivative and then move the dx to the other side. So the derivative would be 5x to the fourth plus 37. Move the dx to the other side, so dy, the differential in y, is equal to 5x to the fourth plus 37 times dx, the differential in x. Okay? We'll talk more about applications of this in section 2, where maybe if I'm making, let's say, round ball bearings, I want to know if I change the radius a little bit, that would be dr, how much will the volume change? Okay? Or if I have an error in the radius of measuring the radius of a round ball bearing, how much will this error be in the volume? Okay, this is where differentials come into play. Sometimes they're called tolerances when we're machining parts. Okay, but don't get confused by that. We'll deal more with that in the application section. Alright, what I want you to do for practice problems is, again, 3.6 part 2 is coming. Those are applications. Work on the following. 313, numbers 1 through 24. This is a pretty easy homework assignment because you guys need a rest. Okay, see ya. Bye.